Hi and hello. This video is on section 2.6, where we're going to sketch a curve given information about limits and points on that curve. Now, I label this sketch a possible curve just to emphasize that there's no one curve or one function that will match these criteria. There's usually just tons of different functions that match these, but you need to be able to draw at least one of them that matches all the criteria at once. So we're drawing one function. It could be piecewise. It could have different branches that may connect or may not connect, but it'll be one function that matches all the criteria that are given. So let's just jump into some examples here. So my first example, example A over here, we have one function where f of 1 is equal to 3. Just to make sure we know this going on, when x is equal to 1, this is the x value, then the y value is 3. So when x is 1, y is 3. The second piece of information says x is really, really close to 2, infinitesimally close to 2 from both sides, left and right, and the y value is infinity. So when x is close to 2, the y goes up to infinity. And that's a positive infinity, my friends. There's a difference between positive infinity and negative infinity. That is a very large positive number as far as you can go upwards for the y values. The third piece of information talks about when x is going to infinity. So now I'm trying to erase this. So now when x is all the way over there, infinitely big, right, all the way to the right, then the y value is 0. Remember, x is over here and y is over here, right? So it's telling us x is infinitely big and y is equal to 0. And the last piece of information says x is approaching negative infinity. Negative numbers are this way. So all the way as far as you can go left, that's where x is going to be negative infinity. We have a y value of 1. So let me draw in some axes here. I'm just going to sketch it by hand. I'm not going to make it fancy. I'm not going to make a grid. I'm just going to do a sketch. I'm just doing a sketch. So we need some x numbers. We know that when x is 1, y is 3. So let me put a 1 here and maybe a 3 up here. And I know that that point, 1 comma 3, actually, let me do it a different color. This point 1 comma 3 has to be part of the function. No matter what, it has to go through that point. All right, the second piece of it, so I'm going to put a little check mark. Yeah, we did f1 equals 3. The second piece of information says when x gets closer and closer to 2, the value of y is infinity. So we need a 2 on this picture. X is 2. This is the x-axis. So this is where x equals 2. And where is y infinity? Well, here's 4 and 5, and infinity is way, way up there. That's where y is infinity. So we want y to be going to infinity when x is going to be 2. So how do we draw that? Usually we draw that as an asymptote. We put kind of a dotted line, not because you have to, but visually it helps humans if we have this sort of, goalpost that we're trying to get closer and closer to. So the y value is getting closer and closer to infinity when x gets closer and closer to 2. So right up here, it's going up to infinity when x is close to 2, and that's on both sides. So it has to go up to infinity. I'll put a little arrow saying all the way up to infinity when x approaches 2 from the left and from the right. This is a two-sided limit, so we have to go from the left and the right. Now, it would be nice if I connect these just because it looks nicer. You don't have to necessarily, but I will connect these two. So it looks like that. And this one, I'm not sure what it does. I'll just go down like that. So that's my graph so far with the first two criteria included. All right, we're up to number 3. Number 3 says we want to know, we want to illustrate when x is infinity this way, y is equal to 0. So we have x, x is 3, x is 4, x is infinity is all the way that way. So we're going all the way that way as far as we can possibly be. The y value is 0. We illustrate this again with an asymptote. These, by the way, are the definitions of horizontal and vertical asymptotes. A vertical asymptote is a value of x that makes y be infinity or negative infinity. And the definition of a horizontal asymptote is a value of y when x is either positive infinity or negative infinity. All right, so x is going all to the right, and we want y to be 0. So this is where y is equal to 0, right here on the axis, same as the x-axis. So we want this, maybe I'll make it a little sharper going down here. We want this function to go down and get closer and closer and closer to y equals 0. So I'll put a little arrow there kind of showing that it goes closer and closer to the y equals 0 line. It takes going to infinity to actually get to 0, but we know we can't really get there, so we'll just put an arrow with a dotted line saying that you get closer and closer there. All right, that's the third criteria. Last criteria, when x is negative infinity, so going all the way that way, we want the y value to get closer and closer and closer to 1. So if you think about that and relate to what we just did, that means the y value is getting closer and closer and closer to 1. So I'm going to write a dotted line here to visually see what happens as x goes to negative infinity. As x goes all the way to negative infinity that way, then the y value is getting closer and closer to 1. And we'll just make this continue on because it's kind of nice. Like this. So there's an example of, and that's the fourth criteria there. So we've done all 4 criteria. This is an example of a function that matches all 4 of those criteria. All right, so that's an example of curve sketching, or sketching a possible curve, giving information about limits and values of the function. All right, well, I just have one more example here, part B, that I'm going to do. Just a reminder to pause the video frequently to see if you can try these yourself. It is a great way if you get actively learning involved in the problems. Well, if you did get a chance to try that, fantastic. I'm going to be showing you my version of the solution. Our graphs may not be identical because remember, there's more than one that fits the criteria. All right, so we do have a gx function here. The first criteria says x is approaching 0 from the right, and the y value is infinity. So again, horizontal axis, we're going to call x, vertical axis, we call y. When x is getting closer and closer and closer to 0 from the right, y is getting closer and closer to infinity. I'll just put a dotted line at 0, and I'll put some arrow up like this. And the reason why I'm going off to the right is because the limit says x has to be greater than 0, right? Getting infinitesimally close to 0, we get y going off to infinity, but it's going to be definitely to the right of 0. So that information tells me this part of the graph, something like that, is what this is going to tell me. Second criteria says when x approaches 0 from the left, then the value of the function is negative infinity. So negative infinity is down, 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 right? The y value is negative infinity. So I'm going to represent that in red like this. So we have y going off to infinity when x is approaching 0 from the right-hand side, and y going off to negative infinity when x is approaching 0 from the left-hand side. All right. Second piece of information incorporated into my picture. Next piece of information says when x is positive infinity, the y value is getting negative 2. So I need a y value of negative 2, negative 2. And this says x is going to positive infinity. So x is going to positive infinity. So the graph is going to the right. And the y value is getting closer and closer to negative 2. So I'll draw my little line in here just as a visual, separation and goalpost. I can see what's happening. The x value is getting closer to infinity, and the y value is getting closer to 2. So I can do that by going down to negative 2 and putting a little arrow saying, oh, yeah, it continues to get closer and closer and closer to this dotted green line here. So that's the third criteria. The last criteria here we have here is x approaching negative infinity, so that way to the negative side, and the y value is supposed to be 3. So we need a 1, 2, 3 up here, and y is getting closer and closer to 3. So let me put a little visual aid here for saying that's 3. And as x goes to negative infinity, as x goes to the left, we need the y value to get closer and closer and closer to 3. So there's an example of a graph that fits these 4 criteria. What they're really hoping here is that you become comfortable with limits and reading off what x and y are going to be, and the asymptotes, if there are any, for functions. So it's an exercise in just becoming comfortable with the notation and limits. It's not really used too much in calculus, this curve sketching thing, but it's a nice little fun exercise to see if you could draw a graph that fits some random criteria. I do have one last aside here, trying to help students not be afraid of things that they have been afraid of in the past, like zero on the denominator, where we were told that we should run away and hide. But we can do a lot of investigations even with zero on the denominator. We can't calculate it, but we could do a lot of things like finding limits and what values are getting closer and closer to. And we can do the same thing with infinity. Infinity is, it's not really a number, but we shouldn't be afraid of it, right? We can do stuff with it. So I have some examples of not being afraid of infinity. So for part C, I have the limit as x approaches infinity of 6 over x. So this is 6 divided by a very, very, very large number. 6 divided by, a million, or I usually use nines, just looks bigger. So 9999999, but I think that's kind of weird, I think, for some people. So I'll do 6 over like, 1, oops, where's my pen? 1 million or trillion or something like that. There's a million. So what happens with 6 divided by a million? Well, that's as a decimal 6 millionths, right? That's a fraction 6 millionths. So it is 0.000006, right? So this is 0.000006. And of course, we could add more zeros, make x be a larger number. Certainly a million is a large number, but nowhere close to infinity. So we can add more zeros here, maybe a billion or a trillion or a quadrillion. And that just makes more zeros onto here. So we have 6 divided by an extremely large number being a very, very small number, right? 6 divided by 100 is 0.06, 6 divided by 1,000 is 0.006, 6 divided by a million is 0.0006, etc. So what happens as x goes to infinity? Well, the answer, the y value, gets closer and closer to 0. So even though we can't really understand infinity as a value because it's not, we know that the limit as x approaches infinity of a number like 6 divided by x is equal to 0. And what about example D here? Example D kind of got written over a little bit there. We have x on the top and 4 on the bottom. So now we're putting in the huge number like the million on the top and 4 on the bottom. And a million divided by 4 is 250,000. But of course, we could get bigger. We could do billions or trillions or quadrillions or quintillions. You're getting this very, very large number divided by 4. The divided by 4 is not going to do much. Yeah, it's going to make it slightly smaller, but the top is getting infinitely big. And you have something infinitely big and you take a little bit off of it, you're still going to have something infinitely big. So this is going to be something like infinity divided by 4, which is going to be infinity. So if you have infinity divided by a number, don't be afraid to analyze what's going on. You can make a table of values, you can make a graph, and you will find out very quickly that the value of the function x over 4 goes off to infinity when x is infinitely large. All right, last couple of examples here. I have a fraction here. We can use our algebra to simplify this fraction. Notice that when I have infinity, on the top, I have something like infinity cubed plus infinity divided by infinity. Now, don't tell anyone I wrote that because math people get very sour when you write like the infinity cube, because infinity is not a number. We can't do operations with infinity. But just between me and you know what's going on, right? We have something infinitely big cube plus in something like infinity divided by infinity. Not precisely in a mathematical way, but definitely, sort of in an intuitive idea, we have these infinity things. Okay, so let's actually do the math. Remember, we can do algebra. We know algebra. So I'm going to simplify this limit by doing factoring or by doing distributive property. I've been doing factoring a bunch recently. So let me go back to doing the distributive property. I'm just distributing by the divided by x. Distributive property works when you have more than one thing added or subtracted, and all of those things are being multiplied or divided by the exact same thing. Here we have two things being added, and they're all being divided by x. So I can write this like this and simplify. And I have x squared plus 1. And once again, we know that x is going to infinity, right? Remember the x infinity part? So this part right here is a very, very large number, 1 million billion trillion squared. So that's going to be like a million billion squared, which is going to be even bigger, bigger, bigger. So this is getting super, super big, infinity. And what's infinity plus 1? Still infinity. So this limit goes off to infinity. Infinity minus 1 is infinity. Infinity divided by 2 is infinity. Infinity plus 1 is infinity. You're not going to be able to get rid of infinity unless you divide by something infinitely large or subtract something infinitely large, right? You're not going to be able to get rid of it by a simple number. All right, lastly, we have letter F here, which is almost exactly the same as E. If you notice F and E, the only difference is the denominator is x plus 1, which makes simplifying a little bit more complicated because now the common divisor is x plus 1. So we'd have to have something like x cubed over x plus 1 plus x over x plus 1. And these become algebraically more complicated to simplify. But nonetheless, I can assure you that we can understand this just by having a bit of insight about infinity. We know infinity plus 1 is still infinity. So on the bottom here, x plus 1 is basically the same thing as infinity plus 1, which we know is still infinity. So I am claiming that the limit as x goes to infinity of x cubed plus x over x plus 1 is approximately the same as the limit we just did with just x on the bottom, because that x plus 1 is not doing anything different than the x is doing. You can codify this in what's called the squeeze theorem. So we're going to learn about the squeeze theorem and do some of this a little bit more, sort of substantially, more precisely. But I want you to sort of see now that we can understand what's going on here. Infinity plus 1, same thing as infinity. This thing becomes essentially equivalent to x cubed plus x over x. And we know what that is. We know what that is from the previous problem. We know that goes to infinity. That's the same problem as over here. So I was just trying to give you some ideas about infinity and not to be so afraid of it. Like in a previous video, I said, don't be afraid of zero or division by zero, multiplication by zero, because I think some students just see that and they want to just like shut down and not even do anymore. It's just time for a little bit more investigation. So, all right, well, that's the end of today's video on section 2.5 or 2.6, excuse me. And hopefully this was helpful to you. And once again, if you have any questions or comments or want additional help or additional practice, just let me know. All right, hope you have a good day.